Hello everyone, today we have lecture 10 and topic will continue our discussion on explanation of corrosion event on the basis of mixed potential theory, and today we will try to see couple of examples. Mainly we will talk about this situation one is if we have 3 cathodic reaction and 1 anodic reaction, and 2 we will take 2 situations today. So, another one is effect of exchange current density on the corrosion of active component. So, these 2 situations we will look at. In this case, it is very clear that we have in a system we have 3 cathodic reactions and 1 anodic reactions. In lecture 8 and 9 we talked about 2 cathodic reactions and 1 anodic reaction. And the second situation we will consider is the effect of exchange current density on the corrosion of active component. So, in this case it could be possible that the cathodic reaction or the anodic reaction that are taking place on that particular metal in that particular environment could be higher than the exchange current density of those cathodic or anodic reactions on that active component. This is one situation. Another situation is we can have in normal circumstance, so that means engineering applications, many a times we have galvanic couples or contacts between active metal side and noble metal side. One classical example is when we have combination of copper and steel, like if we have a steel rivet joining 2 copper plates, that is one combination where the exchange current density of the cathodic reaction on copper surface will be higher than the exchange current density of the cathodic reaction on the steel. So, this is one case. Another case could be platinum. If platinum or gold or palladium, those are noble metals, those are galvanically coupled with or connected to steel or iron. So, that case iron dissolution rate will be much higher in acid, because hydrogen exchange current density on platinum or gold or palladium is few orders magnitude higher than the exchange current density of hydrogen evolution on iron surface. So, that also increases the rate of dissolution of iron. So, we will consider that part. So, the first let us see the situation 1 what we have considered here. So, let us say a situation where we have zinc dissolution in aerated aerated, impure, and the impurity is nothing but Fe plus 3 ion HCl solution in ambient condition. So, that time if this is the consideration, let us say here the situation 1 here. So, we have 3 cathodic reaction, one is H plus 2E equal to H2, 2 is Fe plus 3 plus E equal to Fe, 3 is O2 plus 4H plus 4E equal to 2H2O. So, these are the 3 cathodic reactions. Possible in that particular electrochemical process, and there is only one anodic reaction since zinc is dipped in that particular impure aerated acid. Aerated means it is freely aerated, that means oxygen is there, dissolved oxygen is there. So, that is what this reaction is possible. So, the dissolution reaction, this is the dissolution reaction or anodic reaction, one anodic reaction. So, this is possible. So, that case we have to consider all the reactions over zinc, because that is the only metal surface that all those 3 cathodic reaction will face, as well as of course, this anodic reaction. So, that time we can draw mixed potential theory. This is the plot between log I versus E, which is volt, and we will consider this voltage with reference to standard hydrogen electrode. Now, let us say this is the point which is E equilibrium of zinc corresponding I 0 zinc over zinc surface. Then we will have another reaction which is basically hydrogen evolution reaction on zinc surface. So, this is E equilibrium hydrogen. Then we can have E equilibrium iron plus 3 Fe plus 2, and then we might have another, we will have another one which is E equilibrium O2, and corresponding value, this is I 0 O2 over zinc surface, this is I 0 Fe plus 3 Fe plus 2 over zinc surface, and this is I 0 H2 over zinc surface. So, now all the 3 cathodic reactions we have to consider in order to consider the concept of mixed potential theory, that will reach E mix, where summation of I c equal to summation of I a. So, that condition is to be met. So, this is the mixed potential achievement or concept, mixed potential theory as per the mixed potential theory. So, now we have to extend those lines and then keep adding up those similar lines like cathodic lines, wherever there will be a experience of new reaction while cathodic polarization takes place. So, now if we consider for example, black color for zinc. So, this is my zinc, it will go up like this. Then this will be extension of this. This is hydrogen line, dotted line is the hydrogen line. Let me draw with the blue color the line for iron. So, this is the iron line, but at this point, at this particular voltage, when this Fe plus 3, this particular reaction is polarizing towards cathodic side. So, at this point it will experience another cathodic reaction, which is hydrogen evolution reaction. So, we have to add it. So, I am adding all the things like a blue green color. So, this is the addition part. So, this line is IC total equal to IC hydrogen over zinc surface plus IC Fe plus 3 Fe plus 2 over zinc surface. So, that means if we have no oxygen, dissolved oxygen, but only oxidant, which is a strong oxidant like Fe plus 3, then the mixed potential would be, this one will be mixed potential. A mix when Fe plus 3 is present. Now, we have to consider, let us say, with the purple color. So, if we continue this oxygen line, this is the oxygen line, this is the oxygen line. Now, it will, when the oxygen line is, this cathodic reaction is polarizing, at this potential it will experience another cathodic reaction, which is this one. So, we have to add it. So, if we add that, we add it and then keep going down parallel to the purple line. So, you will come there and then it will. So, if I change this line little shallow, the slope becomes if I change this slope little bit, I have changed the slope little bit, so that I can have the effect of hydrogen polarization also. So, that case this line will have to be changed. So, that the new we just doing little bit of modification. So, this will be my mixed potential when Fe plus 3 is present. Now, at this point when it come to this line, which is hydrogen evolution start point, it will further add it up and then go down. So, this particular line is IC total nu equal to IC hydrogen evolution on zinc surface plus IC Fe plus 3 Fe plus 2 over zinc surface plus IC oxygen over zinc surface. So, this should be equal to, there is only one anodic reaction, IA zinc over zinc surface. Of course, this is not needed at all. We have just put zinc because those are happening on a zinc surface. So, this and the E mix should be so this is the E mix. Let me put it as a prime when we have dissolved oxygen Fe plus 3 in acid. So, we consider, in this case we have considered all those three processes, and in this case we are considering when O2 dissolved oxygen is not present. So, this is my complete diagram, and at this point this is the E mix, and we could see that the total IC equal to total IA, and here only one IA is present, and similarly in this case IC total is basically the combination of two reactions because one reaction is not taking place. Now, we see that as the number of reduction reactions are increasing, I could see that the corrosion rate is increasing. This is I core and this is I core prime. So, I core is corresponding to the situation when Fe plus 3 present and O2 not present, but in this case Fe plus 3 present, O2 present. Now, that means as we increase the number of reduction processes in the complete electrochemical process, which is nothing but the corrosion of zinc, our corrosion rate increases depending on whether these interactions are possible. But there could be a situation like one situation I can think of. So, I will just draw that same line without giving any without writing all those details. This is the zinc one, this is the hydrogen one. I just simply write hydrogen and zinc. This is IA, this is IC hydrogen over zinc. Now, if this is my IC Fe plus 3 Fe plus 2 over zinc, then here I could see that we can have the existence of hydrogen evolution reaction. So, this is the new corrosion point, this is IC total equal to IC hydrogen over zinc surface, hydrogen evolution of course, IC Fe plus 3 Fe plus 2 over zinc surface. But if the another that oxygen evolution reaction happens here depending on the E equilibrium oxygen. So, that will go straight of course, it will be decided by the Tafel slope, and here one assumption is whatever things we are drawing, one assumption is we are considering Tafel slope to be same for either of that cathodic or anodic processes. So, now here we could see that I could add this reaction. I could add this reaction, which is I C total prime equal to I C Fe plus 3 Fe plus 2 plus I C O2 over zinc surface, but before it intersects where it intersects the anodic line. So, that potential, this is the E mix prime, this point is above the hydrogen evolution line on the zinc surface. So, the hydrogen reaction will not be effective here. So, the only two reaction will guide the entire corrosion process. But one more important issue we will see with some numerical problem. If this, since this is in log scale, if this line and this line they are staying quite further from each other, so then the effect of this line on this overall reaction rate of the zinc dissolution will not be felt. So, we will see that part in next class, where we will be solving one problem. Now, this is one typical situation where even though there are 3 cathodic reactions, but one cathodic reaction is not participating, but once we have this situation, there could be addition of another anodic reactions, because beyond this, because this potential is above this potential, this E core is greater than E equilibrium hydrogen. So, we can have addition of oxidation reaction. So, here it will be added up. So, it will go like this. So, this will not be the actual E mix, rather this point will be the E mix. This point will be the E mix, because we could see that when anodic reaction is going up, so we have the anodic reaction for hydrogen is going on. So, this particular line talks about hydrogen minus 2 E equal to H plus. So, at this point I will actually meet the mixed potential concept, which is summation of I C equal to summation of I A, which is nothing but I C hydrogen on, this is Fe plus 3, Fe plus 2, zinc plus I C oxygen reduction on zinc surface equal to I A of zinc over zinc surface, I A of zinc plus I A of hydrogen 2 H plus. So, and that is possible at this point, fine. So, this is the possible changes. In this case I could see that before this mixed potential line, which is basically this situation, which is nothing but E mix prime, before it meets that anodic line of zinc, it actually come across all the polarization, cathodic polarization lines of all three cathodic reactions. But here we see that if the situation is like this, when it reaches to the mixed potential, that potential lies above one of the E equilibrium hydrogen line. So, this is the hydrogen line is staying above. So, we have to add the anodic current density of hydrogen with anodic current density of zinc, and then only we get the concept of mixed potential theory. So, this is one variant for a situation when we have multiple number of cathodic and one anodic reaction. So, let me stop here. We will continue our discussion on this particular topic, and the next class we will talk about effect of exchange current density on the corrosion rate of an active metal. Thank you.